The Interstellar Traveler 3I Atlas has done the unexpected. As it swept through perihelion on October 29, 2025, its glow surged and its color shifted to a hue bluer than the Sun. This is not rumor. Avi and his collaborators report the change, based on independent data from Stereo A, SOHO LASCO C3, and the GO19 coronagraph. Their language is cautious. Their conclusion is clear. They cannot explain what they saw. If this mystery continues to have you hooked the way it has me, make sure to hit like and subscribe so you don't miss a single update as this unfolds in real time. Drop a comment with where you're tuning in from, what time it is there, and what you think of this new development. And if you want to help this community grow, share this video on X, Facebook, Reddit, or even just in your group chats. You're the reason we can keep chasing stories like this. So, thank you for having our back. Behind the Sun, where ground telescopes were blind, coronagraphs had a direct view. Those instruments do the work of masking the solar disk and imaging the faint corona beyond. In those frames, 3I Atlas brightened far faster than any standard model predicts. Photometry across multiple platforms fits a power law with heliocentric distance raised to about -7.5, plus or -1. To put that in scale, if brightness normally follows slopes near -3 to -5, an exponent near -7.5 means brightness scales roughly 2·7.5, on the order of 180 times faster when distance halves. That jump is outside the normal range for cometary physics. The coronagraphs recorded more than intensity. They recorded color. Filter ratios from Stereo A, SOHO, and GO19 place the object measurably bluer than the solar spectrum. Across different optical designs and calibration histories, the instruments converge on the same trend. A large luminous envelope surrounds the object. GO19 measured an extended glow about 300,000 kilometers across. That spans almost 24 Earth diameters. The envelope did not behave like simple scattered sunlight. Its surface brightness and spectral balance point toward emission, not pure reflection. This sequence raises two immediate possibilities. One is that a volatile-rich body from another system underwent extreme, perhaps pressure-triggered, outgassing at perihelion. Supervolatile ices such as CO and CO2, detected earlier by SphereX in August, can drive violent activity. If those ices flashed into massive production under intense solar heating, the coma could flood with molecules that fluoresce in the blue and near UV. The other possibility is more exotic, emission driven by plasma processes, or an unfamiliar material that responds to extreme radiation in ways our catalog does not cover. Some have even sketched the speculative scenario of engineered material that activates under high flux. That hypothesis remains speculative and requires extraordinary evidence. To judge those claims, we must lay the instruments and data bare. Stereo A carries a heliospheric imager and a coronal camera that sample fields at different scales and cadence. SOHO's LASCO C3 contributes decades of calibration history and a wide field. GO19's CCR1 coronagraph offers high cadence, low noise sequences ideal for time series. The three systems do not share optics or detectors. Patterns that persist across them reduce the odds of a single instrument artifact. Still, coronagraph photometry is difficult. Stray light, vignetting, detector nonlinearity, saturation, cosmic rays, background subtraction errors, any of these can bias brightness and color measurements. Teams are already checking raw frames, calibration files, and processing pipelines. Independent reanalyses will decide whether the steep slope and blue shift survive scrutiny. The brightness curve itself demands attention. Before perihelion, ground tracking showed modest activity consistent with normal comet behavior. Near perihelion, the slope steepened abruptly. That transition appears compressed into a narrow window around closest solar approach. Physical triggers exist that can produce rapid brightening. A crust can fracture under thermal stress, exposing volatile rich layers. A nucleus can fragment, multiplying surface area and releasing trapped gases. Fluorescence from abundant molecular species can light the coma. Those mechanisms typically produce transient spikes, not a sustained steep exponent across days and instruments. The data currently read as sustained. That creates tension between model and observation. Color offers another constraint. The sun's visible output peaks near yellow-green. Reflected sunlight off neutral dust tends to mirror that spectrum. Blue excess implies either scattering by submicron grains, strong molecular emission bands such as CN or C2, or plasma-driven line emission from excited ions and atoms. CN emits near the near UV and violet. C2 can give green-blue bands. Submicron Rayleigh-type scattering favors shorter wavelengths. Plasma excitation by solar wind electrons can drive visible emission under the right densities and geometries. In 3I Atlas, the blue signal extends across a coma scaled to hundreds of thousands of kilometers. Typical cyanogen and diatomic carbon emissions dominate much smaller inner comae. Producing blue emission at that spatial scale requires either prodigious production rates or a different emission mechanism. Other anomalies complicate the picture. Observers reported an antitail that grew from roughly 600 to 720 kilometers in 24 hours. Astrometry registered small residuals from pure gravitational motion, fractions of an arcsecond, reported as shifts near plus 0.37 arcsec rising to about plus 0.43 arcsec. Some datasets suggested little perihelion flare while coronagraphs captured dramatic changes. These are not trivial inconsistencies. They may reflect different instruments sampling different physical regimes. Coronagraphs catch extended, faint emission in the near-Sun environment. Ground telescopes resolve inner coma structure and tail morphology. Astrometric residuals can arise from asymmetric outgassing jets or isotropic emission that produces little net thrust. The history of interstellar visitors offers context. Oumuamua produced unexplained non-gravitational acceleration without clear outgassing signatures. 2I Borisov behaved like a typical comet. 3I Atlas now sits apart from both. Bright emission without an obvious match in non-gravitational thrust. Skepticism is the responsible posture. Instrument teams do not rush to claim discovery. They run checks. They test for saturation effects that clip pixel values. They model stray light and vignetting. They reject cosmic ray artifacts through temporal coherence. They compare independent pipelines. If the steep brightness law and the blue index survive those tests, the result will push models hard. If the patterns collapse under calibration scrutiny, the episode will join past false alarms that taught teams where instruments can mislead. What would genuine confirmation look like? Convergent, independent lines of evidence. High-resolution spectroscopy that identifies emission lines inconsistent with known comet chemistry. Infrared signatures that match CO or CO2 bands at specific flux levels. Polarimetry that constrains grain size and plasma behavior. High-cadence imaging that links variability to solar wind drivers. Radar or resolved imaging that reveals structure incompatible with a rubble pile nucleus. And non-gravitational accelerations that track mass loss histories or their absence that argues for emission without thrust. There are 3 hypothesis frameworks to test. Hypothesis A, a natural supervolatile comet, rich in CO and CO2, that underwent extreme outgassing and fluorescence. Hypothesis B, an exotic natural process, such as plasma-driven emission, dust grain luminescence, or magnetic coupling to the solar wind. Hypothesis C, activation of engineered material whose response appears under intense radiation. Each framework offers predictions and tests. Each carries different implications for follow-up observations. Whatever the outcome, the next months matter. 3I Atlas will re-enter view on December 19th. Observatories worldwide will be ready. Spectrographs, narrowband images, UV and IR assets, and high-cadence photometers will assemble data. Amateur analysts will download raw frames. Peer review will weigh claims against calibration checks. The community will either extend cometary taxonomy or close a gap that opened under difficult observational geometry. This is a story that sits between discovery and confirmation. The instruments reported an event that challenges expectations. The science process will determine whether the anomaly endures. Listen to the data. Watch what the telescopes say next. The instruments have spoken. Now the field must test what they heard. The instruments have spoken. Now the world waits for the verdict. In science, waiting can feel like orbiting uncertainty itself, suspended between discovery and doubt. The signals from 3I Atlas are still echoing through data centers across the planet, raw telemetry packed in terabytes of coronagraph imagery, photometric logs, and spectral ratios. Each number holds a piece of a mystery that may redefine what we think drifts between the stars. Right now, every major observatory with a clear line of sight to the inner solar system has queued time for mid-December. The Hubble Space Telescope, still running on its stabilized gyros, is preparing a narrowband campaign to target emission lines between 380 and 520 nanometers. The James Webb Space Telescope will aim its mid-infrared spectrometer toward the coordinates of re-emergence, searching for CO and co-signatures. ESA's solar orbiter will cross-check flux fluctuations in the same timeframe, using its ultraviolet imager to test whether the object continues to glow blue under less extreme solar exposure. Across these missions, calibration specialists work through long nights. Their task is simple in phrasing, monumental in execution: prove that what we saw is real. At the Naval Research Laboratory, the LASCO C3 calibration files are being reprocessed from the ground up. Engineers are reconstructing the instrument's point spread function using flat field archives dating back a decade. The goal is to rule out vignetting, a gradual falloff in detector sensitivity that can skew color readings. At NASA's Goddard Space Flight Center, the Stereo A team is applying new destriping algorithms to separate cosmic ray noise from faint sources. In Colorado, NOAA analysts are combing through GO-19's telemetry for temperature drifts in the CCD array. Even a 1-degree rise could alter response curves across filters and mimic color change. Every scientist involved knows what's at stake. If the blue shift holds up under this level of scrutiny, it implies physical processes operating at energies or chemistries beyond known cometary behavior. If it collapses, the story ends as an elegant failure of measurement, another reminder that the cosmos always tests our instruments first, our imagination second. In research meetings and private video calls, debates stretch late into the night. Some argue the anomaly will dissolve under calibration corrections. Others, quietly, think the opposite. The data, they say, are too consistent across independent sensors. Too coherent. Too synchronized to be coincidence. At the University of Hawaii, Comet researcher M. Onega describes it plainly. We've never seen 3 independent spacecraft agree on an error. At the Harvard-Smithsonian Center for Astrophysics, Avi Loeb and his group continue to analyze the photometry using Bayesian fitting models. The slope remains near -7.4. The blue color index remains negative by multiple sigma. Unclear, Loeb says again, but his tone has shifted. Not disbelief, curiosity. The kind that makes careers and enemies in equal measure. The tension isn't about data anymore. It's about interpretation. If 3I Atlas is natural, it's extraordinary. A supervolatile comet from another system that carries chemistry alien to the solar system. If it's not natural, the implications move from science into philosophy. What if the universe is older not just in time, but in technology? What if debris can outlive civilizations, drifting silently between stars, reawakening when the light of a new sun falls on its surface? Those are questions few researchers will voice on record. Not because they lack imagination, but because they understand how fragile credibility can be when the public listens too closely. Still, whispers travel. Inside the European Southern Observatory Slack channels, one researcher posts a quote from Clark: "Any sufficiently advanced technology is indistinguishable from magic." Someone replies, "Unless your magic saturates the CCD." Humor is the scientist's way of managing uncertainty. The reality is colder, slower, and more disciplined than imagination. Peer review will take months. Data must pass statistical thresholds. The threshold must survive replication. Then, and only then, can a sentence change from remains unclear to cannot be explained by current models. Yet science does not happen in a vacuum, and neither does public curiosity. On social media, hashtags spread faster than data. #BlueComet trends for days. Amateur astronomers post animations comparing coronagraph frames. Some see patterns that aren't there. Some catch real motion that professionals later confirm. Citizen scientists feed the conversation, expanding it beyond the institutions. In Lagos, in Warsaw, in Seoul, people wake up before dawn and point small telescopes at the region of sky where 3I Atlas will reappear. They won't see it yet, the solar glare still hides it, but they want to be first when it does. For the first time since Oumuamua, the public feels like it's watching science in motion, not in retrospect. Meanwhile, inside data centers, machine learning models run comparisons across thousands of known comet spectra. The algorithms search for spectral fingerprints, molecular band patterns, and intensity ratios that match the reported observations. So far, none fit. The output cluster for 3I Atlas sits alone, a statistical island surrounded by empty parameter space. If this pattern holds, the consequences ripple outward. Not catastrophic, but paradigm-shifting. Cometary science, long a stable field, would need to rewrite its formation models. The chemistry of interstellar ice could no longer be considered universal. At the same time, engineers would gain a new challenge: understanding materials capable of surviving intense solar radiation while emitting in short wavelengths. Astrophysicists would ask what this means for exosystem formation. Philosophers would ask what it means for intelligence. Because deep down, behind the scientific rigor, that question lingers like static. What if this thing isn't reacting? What if it's responding? No one will say it outright, but the thought pattern repeats across private discussions. Every new signal from space forces humanity to measure itself. The rational response is always the same: collect more data. The emotional response is older: awe, unease, anticipation. 5 weeks separate the observation window from re-emergence. In those weeks, astronomers will align global resources. The Very Large Telescope in Chile will monitor visible bands. The Subaru telescope will image near-infrared spectra. The Solar Dynamics Observatory will provide context of solar wind conditions. Even small robotic scopes in desert arrays will record photometric baselines for correlation. By mid-December, a data mosaic will form. Every pixel, every photon, every timestamp will feed into a larger picture. Whether that picture reveals an exotic chemical reaction or the remnants of something constructed long ago, it will mark a milestone. If confirmed, the implications reach beyond astronomy. It touches everything: our theories of cosmic evolution, our definitions of life, our concept of solitude in the galaxy. Because if 3I Atlas is artificial, even in the smallest sense a fragment of material designed elsewhere, then it means technology has crossed interstellar distances without its makers. A silent testimony drifting through space, outliving the hands that built it. But for now, that remains speculation. In the sterile light of mission control rooms, scientists stare at screens that display columns of numbers, not meaning. They know the difference between wonder and evidence. They've seen the sky deceive before. And yet, this case feels different. Because the data, as incomplete as it is, carries coherence. Because 3 independent spacecraft watched the same impossible thing. Because the blue color still resists erasure. The next act begins in silence, the kind that precedes revelation or disappointment. At Harvard, Loeb's team readies a preprint titled Photometric and Spectral Anomalies in the Perihelion Passage of 3I Atlas. The abstract ends with one sentence. The observations, if validated, require revision of current models of cometary photometry or the consideration of non-natural emissive processes. At NASA, an internal memo circulates. Prepare for possible anomalous re-emergence event around December 18th to 21st. Coordinate with ESA for real-time cross-verification. At the European Space Agency, Solar Orbiter's imaging cadence is adjusted to capture the predicted position every 6 minutes. In Tokyo, the National Astronomical Observatory drafts a proposal for emergency telescope time on Subaru. They know the world will be watching. When December 19th arrives, Earth's rotation will make observation windows brief. The first images will come from the southern hemisphere. Then the sequence will move westward: Chile, Hawaii, Mexico, California, then the Canary Islands. A wave of data chasing the twilight line. If 3I Atlas reappears unchanged, still bright, still blue, the debate ends. If it fades to a neutral color and stable luminosity, the anomaly may collapse under natural explanation. If it changes again, unpredictably, the story deepens. For the scientists, that day will be another line in a spreadsheet. For the rest of the world, it could be history in the making. Imagine the scene. A control room at midnight. Screens flicker. An operator calls out a timestamp. A faint trace appears on the feed. A shape, a glow, not much more. Yet every person in that room knows they are the first humans to see an interstellar traveler return from behind the sun, carrying with it a question older than civilization. Are we the only ones building things that shine? If the object stabilizes and remains blue, spectroscopy will take over. Lines at 380, 430, and 500 nanometers will tell the story. CN bands mean gas emission. Smooth curves mean reflection. Sharp, narrow spikes in unnatural ratios mean something else entirely. The world will not wait for the papers. Newsrooms already have drafts titled Alien Comet and The Blue Visitor. But the scientists will move slower. They will remind everyone that extraordinary claims require extraordinary proof. They will publish numbers, not narratives. And yet, even they will feel it, that tremor in the collective imagination when a familiar sky starts to behave differently. The story of 3I Atlas may still end as calibration error. But every investigation, every sleepless night in data labs, every discussion on what light can mean, drives us closer to understanding how little we know. Because the truth is, the universe doesn't hand us answers. It hands us signals and waits to see if we're patient enough to interpret them. 5 weeks. Then the next transmission from the interstellar traveler. Until then, every photon recorded, every recalibrated frame, every sleepless scientist will orbit one question. What, exactly, is glowing behind our sun and why? December 19th, 2025. The night Earth turns its telescopes back toward the sun's edge, waiting for what might reappear. 5 weeks of silence end here. At 3:11 Universal Time Coordinated, the first signal comes from the solar orbiter's extreme ultraviolet imager. A dim pulse on the edge of the coronagraph field. Faint, but real. The automated filter flags the coordinates, 94 cents from the Sun, magnitude plus 7.4, spectral tilt still negative, still blue. Within minutes, the alert ripples through mission control rooms around the world. GO19 confirms it. Then Stereo A. Then, hours later, SOHO. 3 confirmations, again. 3I Atlas has returned. And it's still glowing blue. But this time, something is different. The luminosity doesn't climb. It oscillates. A rhythmic fluctuation, rising and falling every 11 minutes, amplitude stable within 0.03 magnitudes. At first, analysts assume thermal modulation, some cyclical outgassing or rotation effect. But when they align the light curve across instruments, the phase is identical. Perfectly synchronized across different spacecraft, separated by millions of kilometers. Coincidence? Possibly. But synchronized periodicity across multiple sensors defies random noise. By dawn in Chile, the first ground-based observatories take over. The Atacama Large Millimeter Array locks in. Then the VLT. Then amateur telescopes in South Africa begin live-streaming the sky. A faint azure glow flickers just above the solar glare, barely visible but steady. The world sees it. And the world starts asking again, what is this thing? At NASA's Jet Propulsion Laboratory, real-time spectrographs start populating the monitor. Co-bands? Yes. Weak but visible. Cyanogen lines? Faint, too faint to drive that brightness. Then a new feature appears, a narrow emission spike at 410 nanometers, sharp as a laser, not matching any known cometary molecule. In mission chat threads, someone types what everyone's thinking. That's not natural. The reply is cautious. Not proven yet. Spectra don't lie, but they also don't explain. The periodic pulsing continues through the day. At the European Space Operations Center, teams cross-correlate solar wind data. No matching variation. The flux from the Sun is steady. The pulse is coming from the object itself. Rotation? Maybe. A slow tumble could modulate light curves. But 11 minutes? That's fast for a kilometer-scale body, fast enough to tear it apart unless it's solid metal or bonded material. Whatever 3I Atlas is, it's holding together under forces that should destroy ice and rock. By now, the story has escaped the labs. News networks run continuous coverage. The phrase blue comet becomes headline shorthand. Anchors try to explain power law exponents and heliocentric distances to audiences glued to glowing screens. Every few hours, a new image appears, a pale sphere wrapped in faint blue haze, hanging near the sun's edge like an unblinking eye. Governments issue no statements, but agencies coordinate behind the scenes. NASA, ESA, JAXA, and ISRO share data over encrypted links. Privately, they debate contingency protocols. Publicly, they insist it's still a comet. But in university corridors, something shifts. Lectures that would have dismissed such speculation now open with caveats. Because science doesn't run on belief. It runs on evidence. And the evidence refuses to behave. Hubble's narrowband filters return the most surprising result yet. The blue signature isn't continuous. It's quantized. The light spikes sharply at discrete intervals, almost digital. Webb's mid-infrared spectrometer adds another layer. Faint, periodic IR flashes at 4.3 microns, the same band where CO should fluoresce, but pulsed in perfect sync with the optical rhythm. Whatever the cause, 3I Atlas is modulating its light, across multiple wavelengths, in repeating cycles. In the following 48 hours, the data flood becomes overwhelming. Every telescope with a clear sky joins the effort. Hundreds of amateur astronomers submit observations. GitHub repositories overflow with raw photometric data. Forums fill with citizen analysis, overlaying light curves, comparing timestamps, arguing whether the rhythm encodes information. Most scientists stay silent. But the few who speak sound cautious, tired, and strangely humble. Because they've seen this before, not this exact phenomenon, but the pattern of discovery. Something that begins as anomaly, becomes obsession, then splits into camps, skeptics and believers, data and dream. By the fourth day, the periodicity begins to drift. The pulses stretch. 11 minutes becomes 12. Then 13. The color shifts from deep blue toward pale cyan. Emission lines flatten. Brightness drops. By December 24th, 3I Atlas stabilizes into what looks like a typical comet tail, still faintly blue, but no longer pulsing. Just light, dust, and gas, the comfort zone of astrophysics. Many breathe easier. The anomaly, they think, has decayed. A rare chemical outburst, now fading. A mystery closing itself. But the data archives don't forget. In the following weeks, independent teams publish preliminary analyses. Each paper adds fragments. One confirms that the light oscillations were real and coherent across sensors. Another notes that no known plasma or dust mechanism can sustain that exact frequency without external modulation. A third confirms that the 410 nanometer line remains unexplained by known molecules. None call it artificial. None call it alien. They call it unresolved. A new word enters circulation: Atlas-class anomalies. A term for interstellar visitors whose photometric or spectral behavior defies natural explanation but lacks direct evidence of technology. It joins the lexicon beside Oumuamua-like objects and Borisov-type comets. Science adapts by naming what it cannot yet define. Months pass. Papers stack. Hypotheses multiply. Some hold that 3I Atlas carried frozen oxygen isotopes with fluorescent cross-sections that mimic blue emission. Others argue for magnetic luminescence triggered by solar wind coupling. A few propose quantum excitation effects in exotic ices formed under interstellar radiation. And then there are those who leave a quiet asterisk at the end of their conclusion. Alternative non-natural processes cannot be excluded. In the background, a more profound realization begins to form. Not that 3I Atlas was built, but that it forces us to re-examine how we recognize design at all. What defines natural versus artificial when chemistry and physics can imitate intention? At what point does pattern become message? These are not equations. They are thresholds. And 3I Atlas has brought humanity to one. In March 2026, a new observation surprises everyone. The object, now outbound past Mars's orbit, brightens again, faintly, rhythmically, as if answering the same pattern that began months earlier. It lasts only a few hours, then fades beyond detection. No one can confirm whether it was real or noise. But for those who saw the data flash across their screens, it felt like a goodbye. Astronomy is built on patience. The universe reveals its secrets slowly, sometimes over centuries. But every once in a while, it sends a messenger that makes us question the rules. 3I Atlas did that. It didn't bring proof of life beyond Earth. It brought proof of how fragile our certainty can be. And maybe that's what interstellar visitors are meant to do, not to answer, but to remind us that the sky is still capable of surprise. When future generations look back at this era, they may not remember the light curves or spectral slopes. They'll remember the question we asked when the sun's own color was challenged by something bluer, colder, and older than we could explain. They'll remember how we turned our instruments toward that light and asked, "Are we sure we understand what we're seeing?" Because every civilization needs moments that force it to look again. Moments when knowledge trembles and grows. 3I Atlas has already begun that process. It may be nothing more than ice and radiation. It may be something far beyond both. But either way, as it fades into the deep dark beyond Mars, one truth remains. Something from another star came close enough to mirror our sun and remind us that the unknown still glows. And in that glow, reflected off a billion silent dust grains, humanity saw itself small, curious, and still searching. The story of 3I Atlas isn't over. It's only receding. For now. The blue light faded months ago. Yet its echo still travels, not through space, but through people. Through the slow machinery of science, through late-night arguments in dim observatories, through classrooms where professors now begin lectures with a new sentence, we don't fully understand 3I Atlas. In the end, it left no message. No pattern that spelled out meaning. Only data. Only questions. But sometimes, questions are more enduring than answers. At the Harvard Smithsonian Center for Astrophysics, a new group of graduate students sifts through archived telemetry, refining algorithms that can detect faint rhythmic modulations. They call it the Atlas filter. It's designed not to find aliens, but to find anomalies. To listen differently. At the European Space Agency, plans take shape for a dedicated deep solar coronagraph, an instrument built to track future interstellar visitors without losing them in the sun's glare. Engineers propose calling it Project Horizon. Others prefer Atlas Watch. At NASA's Jet Propulsion Laboratory, a quiet proposal begins to circulate, a small, autonomous probe designed for interception missions. The idea is simple: next time an interstellar object enters the solar system, launch something fast enough to meet it, not just watch it pass. For years this was fantasy. After 3I Atlas, it's strategy. Even the skeptics have shifted tone. They no longer argue whether 3I Atlas was extraordinary. They argue only about how extraordinary. Because in the hard light of analysis, the facts still stand. 3 independent spacecraft observed a brightness curve far steeper than models allow. 3 instruments recorded a color index bluer than the sun. And the object emitted light with a structure that, while not proof of design, remains unexplained. That is what science calls evidence. Not conclusion, not conviction, but weight. Years from now, when textbooks condense this story into a few paragraphs, they will use clinical phrasing. 3I Atlas exhibited anomalous photometric and spectral properties during perihelion in late 2025. Subsequent observations did not confirm artificial origin. The words will be tidy, but those who lived through it will remember the feeling, the quiet unease of realizing that something beyond our world behaved in a way that our equations could not predict. And that feeling matters. Because science, at its core, is not certainty. It's humility. The willingness to admit when the universe surprises you. In the months following the event, philosophy departments began hosting joint lectures with astrophysicists. The topic was never aliens. It was recognition. What does recognition mean when all you have are photons? When does coincidence become communication? How do you distinguish curiosity from projection? The answers varied, but one phrase kept returning: we looked, and we learned to look better. In Lagos, a group of students started a community astronomy project called Blue Shift, teaching kids how to build simple spectroscopes from discarded CDS. In Mumbai, an artist painted murals of 3I Atlas, a streak of blue over orange horizons. In Kyoto, a poet wrote, "A comet bluer than the sun whispered nothing and we called it proof." Across the planet, the story spread beyond science into art, into thought, into the quiet corners where meaning hides when certainty fails. Because even if 3I Atlas was only ice, it was ice that made us listen. And if it was more, if it was something built, something sent, something ancient, then its builders achieved something profound. They made strangers stop and look up again. When the Voyager probes left our solar system, they carried a message, gold plates etched with sounds and images of Earth. A fragile attempt at introduction. What if 3i Atlas was the inverse of that gesture? What if we were never meant to understand it, only to notice? For now, it drifts beyond Mars, past the orbit of Jupiter, heading for the cold beyond where sunlight is thin and memory fades into the background hiss of the universe. Its trail is gone. Its brightness, silent. But every data frame, every spectral line, every oscillation, all of it remains, copied in servers, printed in papers, encoded in the collective curiosity of a species that refuses to stop asking. In a way, the light of 3i Atlas never vanished. It transformed from blue photons into thought, from numbers into possibility, from a visitor into a mirror. Because in chasing that glow, humanity caught a reflection of itself. A civilization reaching out into the dark, wondering who else once did the same. And so the story closes not with an answer, but with a question that has outlived every age of science. When we see something new in the sky, something that behaves as if it knows we're watching, are we discovering it? Or is it discovering us? The instruments rest now. The telescopes move on to other targets.